The Kuwait International Airport has been designed by Foster and Partners in London to become the next generation of terminals, and it is based on a parametric approach to architecture. So the whole geometry is varying through the airport. And this is of course challenging as engineers. We've been taking over after tender contracted by the general contractor, Limak Kuwait, in order to make this vision and this design possible and buildable. The point about doing that was to generate a workflow that allows to set a parametric engineering on the basis of the parametric architecture, and to make sure that the workflow is going from the engineering process through the geometrical control into the fabrication in a direct way. Doing that together with a production which is set directly on the site allows for a high degree of precision, even with difficult weather conditions as it is in Kuwait. And the client, the Ministry of Public Works in Kuwait, has been supporting the overall process and has been always a good partner in allowing for new technologies to be developed on site. The key was then to carry a model with a collaboration of different partners and use this model to drive the fabrication. The site work has been started in 2016, and by having the process streamlined in this way, it was possible to have a quick production and a quick erection, which was very important for the client to be achieved, despite the complexity of the geometry and the challenging structure. I would like to focus on the two main components of the structure of the airport, because this has been the most challenging part. On one side, the backbone of the system, which is built out of 823 precast elements, creating the arch system built in spines and ribs, and the roofing made out of steel and concrete element, the so-called shell cassette. Just to have an impression about sizes, which plays a role here, we have precast element which weighs up to 340 tons and free spans up to 120 meters. So this is one of the key of this project. Just the size and the complexity of it is required to develop solutions, and it was our role to make sure that there is a high control of every single component and there is a high level of precision in the fabrication, despite the time constraints, and of course it's a real project, the economical constraints. So out of a 3D model of all the different elements, the rebars have been modeled, the embeds, which are build the interface between the concrete and the shell cassette and the roofing. All of that has been integrated to make sure that there is no clashes, that the systems are working in terms of load-bearing capacity, that they are constructible. All of this has been checked and has been led down to the build condition. What was relevant for the speed of the site was to allow for the molding to be reused, and this is of course also an ecological aspect to that, to reuse the same molding again and again with different geometries. So in the molding of the arch, this has been done together with the company Pakadar with an inch segmental system so that the formwork could be adapted. If we look further into the challenges of the shell cassette of the roofing system, we are talking, just to have an idea, about 320,000 square meters and 37,000 elements, and just a degree of repetition of 6. That means 6,000 different geometries. But it's not only about the geometry. All of these elements have been are loaded in a different ways. So here the engineering and the parametric approach to engineering has played a key role to be sure that the right thickness and the right heights of the elements are placed on the right place. The cassettes are made out of steel plates and concrete. Further details can be found in the paper. And the challenging part of that was to generate the engineering by means of scripting. So there's not been single checks, but there has been custom master systems, and out of that then a very detailed model for every single cassette could be generated, as it can be seen in the images. And the fabrication behind it, so the use of innovative welding technologies, for instance, for the cross elements, has been allowing to reach a very high degree of precision. Just to have an idea, we are talking about less than 1 millimeter out of a surface which covers 10 square meters. The last challenge was to make the curvature of the panels, of the cassettes, possible. And 6,000 geometries once again, and this was possible in a collaboration between the general contractor Limac as a structural engineer and Adapa as a subcontractor. So only 85 molds have been required. The specificity of these molds is that they have hydraulic cylinders so that they can adjust to different geometries. And by doing that, the same mold can be reused and reused up to 3 times in a day in order to produce the cassettes in a very, very quick way. So just within a year, all the 37,000 cassettes could be produced. The production is almost completed now for this part, and the erection is a bit affected by Corona, but still the method which has been used shows that the use of digital tools in fabrication, together with a proper engineering, can represent the next step in terms of complex architecture to be achieved within a time frame and an economic frame, which makes this competitive in the market. Because this is, at the end of the day, of course, the challenge that all us as professionals have to deal with. And we believe that this key chain in terms of tight cooperation between architects, engineering, construction, streamlined on the basis of digital process and digital fabrication are the key to allow for much more to come over the next years.